In this lecture, we are going to learn properties of eigenvalues and eigenvectors and problems on these properties. So, first property was the sum of the eigenvalues is equal to trace of the matrix A. So, if you take any matrix A, let it be n by n, right? So, how many eigenvalues you can find? You can find n eigenvalues. Let them be lambda 1, lambda 2, and so on, lambda n. So this property tells us that sum of the eigenvalues, that means lambda 1 plus lambda 2 plus and so on plus lambda n is equal to trace of the matrix A. Okay, what is the trace? Trace is sum of the principal diagonal elements. If you add all these elements, you will get the trace of the matrix, right? So therefore, sum of eigenvalues is equal to trace of the given matrix. This is first property. Coming to the second property, product of the eigenvalues is equal to determinant of A. So product of the eigenvalues, you can write product pi I, pi, right? Pi means product, I equal to 1 to n. So this is product of eigenvalues, lambda 1 into lambda 2 into up to lambda n. So if you multiply all these, you will get determinant of A, determinant of A. So if one of the eigenvalues is equal to 0, what happens? The product becomes 0 and that becomes 0. So if any of the eigenvalue is 0 means the determinant of the given matrix is 0. That is one clue. Coming to the property number 3, A and its transpose have the same eigenvalues. So you are given a matrix for suppose 1, 3, 5, 7 is A. Then what is A transpose? A transpose is 1, 3, 5, 7 written as columns. So these two matrices have the same eigenvalues, right? The same eigenvalues. So transpose, taking the transpose does not affect the eigenvalues. That is third property. Coming to the fourth property, the eigenvalues of a triangular matrix are just the diagonal elements of the matrix. That means, what do you mean by triangular matrix? It can be a lower triangular matrix or upper triangular matrix. If it is a lower triangular matrix means what? Suppose this is the principal diagonal, right? So if all the entries below the principal diagonal are zeros, right? 0, 0, 0 like that. Okay. Then it is called upper triangular matrix. If all the entries above the principal diagonal are zeros, then it is called lower triangular matrix. So in both the cases, we call it a triangular matrix. For a triangular matrix, what the property is telling us is the diagonal elements are nothing but the eigenvalues of the matrix. So if you take the diagonal entries, they are nothing but the eigenvalues of the given matrix. So you need not find, when it is a triangular matrix, you need not find the eigenvalues. Directly you can take the principal diagonal elements as eigenvalues. Coming to the property number 5, the eigenvalues of an idempotent matrix are either 0 or unity. What is an idempotent matrix? It is A square equal to A. So for any matrix, if A square equal to A, then what can you say about the eigenvalues of that matrix? Either zeros or ones. You can't find any other number as a eigenvalue. Eigenvalues will be either zeros or ones for an idempotent matrix. So if you are given a matrix A, suppose the one of the eigenvalues is lambda, then you can find the eigenvalues of A inverse. They are nothing but 1 by lambda. You just take the reciprocal of the eigenvalues of A, you will get eigenvalues of A inverse. The most important thing here is there should not be any zero, right? There should not be any zero. So if 0 is one of the eigenvalues of the matrix A, then you cannot find the eigenvalues of A inverse, right? You cannot take the reciprocal. That means, because that is why you cannot find the inverse of the matrix. Okay. If 0 is one of the eigenvalues, then what happens? In the second property, we have seen det becomes 0. Det A becomes 0. If det A is 0, you cannot find the inverse because it is a singular matrix. For non-singular matrix only you can find. So, if you know the eigenvalues of A, you can find the eigenvalues of A inverse by taking the reciprocal. Coming to the property number 7, if lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also an eigenvalue of the same matrix. That means if A is orthogonal, suppose A is orthogonal matrix, then if lambda is an eigenvalue of A, then 1 by lambda is also an eigenvalue of the same matrix A. Not in the like a previous. Here, in property 6, lambda is an eigenvalue of A, 1 by lambda is an eigenvalue of A inverse. But here, if A is an orthogonal matrix, then what happens? Lambda is an eigenvalue of A, then 1 by lambda is also an eigenvalue of A, the same matrix A. So, suppose 2 is an eigenvalue of A, definitely you can tell about the other eigenvalue. 1 by 2 should be an eigenvalue of A, right? Now, coming to property number 8, if lambda is an eigenvalue of A, then lambda power k is an eigenvalue of A power k, right? So, if you know A square matrix, you can find A square, you can find A cube. So, all these matrices are different matrices. So, every matrix has different eigenvalues. But if you know the eigenvalues of A, you need not find the eigenvalues of A square and A cube and so on, A power k, right? So, they are simply A lambda power k. So, if you know the eigenvalues of A, that is lambda, then lambda power k gives the eigenvalues of A power k, right? So, also k into lambda is an eigenvalue of ka. That means you can find 2a or 3a or 4a. So, all these matrices are actually different. So, every matrix has different eigenvalues. But if you know the eigenvalues of A as lambda, you need not find the eigenvalues of 2A. They are nothing but 2 times the eigenvalues of A. This is 3A, 3 lambda, 4 lambda, and so on. So K lambda eigenvalues are nothing but, so Ka eigenvalues are nothing but K lambdas. Okay. So these are the properties of eigenvalues. Now let us solve some problems based on the eigenvalues. Before that, let us see this concept, right? If lambda is an eigenvalue of a non-singular matrix, what is a non-singular matrix? If that is not equal to 0, we call it as a non-singular matrix, right? A is non-singular. We call it non-singular matrix. That means A inverse exists. A inverse exists. So therefore, how can you write A inverse? A inverse can be written as adjoint A by det A. So why should we write like this? Because you are asked to find the eigenvalues of adjoint A. Right? So you can find the eigenvalues of adjoint A by using the eigenvalues of A inverse. Right? So how do you write? From this you can write adjoint A equal to det A into A inverse. Right? Det A into A inverse. Det A is a constant. It's like a K into A inverse. Right? So if you know the eigenvalues as lambda, you can find the eigenvalues of A inverse, which are 1 by lambda. And you can find the eigenvalues of K into A inverse as K into 1 by lambda, which is K by lambda. So these will come from the properties of eigenvalues just now we have seen. So therefore, what are the eigenvalues of adjoint A? Adjoint A eigenvalues are nothing but k into 1 by lambda, which are k by lambdas. K by lambdas. So eigenvalues of A are lambda I. Then eigenvalues of adjoint A are k by lambda I. I equal to 1 to and so on n. Now let us see a problem. So if you see this problem, A equal to 234042003, you are asked to find the eigenvalues of adjoint A and A square minus 2A plus I. Right? So what are the eigenvalues of the eigenvalues of A, or what are the eigenvalues of A? Because A is a triangular matrix, it is an upper triangular matrix. Below the principal diagonal, lower triangle is 0, means it is an upper triangular matrix. So whether it is upper triangular or lower triangular, the eigenvalues of a triangular matrix are the diagonal entries. It's diagonal, principal diagonal entries. What are the principal diagonal numbers? It is 2, 4, 3. So it is 2, 4, 3. I write 2, 3, 4. Right? So eigenvalues are 2, 3, 4 of A. Then how do you find the eigenvalues? The eigenvalues of adjoint A, just now we have seen, right? Adjoint A are det A by lambda. You name this as lambda, then they are det A by lambda. So what is det A? How do you get det A here? Det A is nothing but product of eigenvalues, because it is a 3 by 3 matrix. You have 3 eigenvalues. Product of the eigenvalues, this is the second property. From the second property, you can find the determinant of A using the eigenvalues. It is 2 into 3 into 4. 24. So det A is 24. Therefore, the eigenvalues are det A by lambda, which are 24 by 2, 24 by 3, 24 by 4. 24 by lambda 1, 24 by lambda 2, 24 by lambda 3. So which are nothing but 12, 8 and 6. So therefore the eigenvalues of adjoint A eigenvalues are 6, 8, 12. You need not find the adjoint A to find the eigenvalues. So you can find the eigenvalues of A square minus 2A plus I. So how do you find A square minus 2A plus I? So what are the eigenvalues of A are 2, 3, 4. Then what are the eigenvalues of A square minus 2A plus I? The lambda square minus 2 lambda plus 1. You replace I by 1, identity matrix by 1, and replace A by lambda. You will get the eigenvalues of A square minus 2A plus I. So they are nothing but lambda 1 square minus 2 lambda 1 plus 1. It is lambda 1 is 2. 2 square minus 2 into 2 plus 1. 1. Lambda 2 square minus 2 lambda 2 plus 1. Lambda 2 is 3. 3 square minus 2 into 3 plus 1. It is 4. And lambda 3 square minus 2 lambda 3 plus 1. It is 4 square minus 2 into 4 plus 1. Which is 16 minus 8, 8 plus 1, 9. So therefore, the eigenvalues of A square minus 2A plus I are 1, 4, 9. Right? They are nothing but 1, 4, 9. 1, 4, 9. Okay. Now coming to the next problem. the two eigenvalues of A are equal to 1 each, right? Then find the eigenvalues of A inverse. Now what you are given here, you are given two of the eigenvalues. How many eigenvalues A has? The eigenvalues of eigenvalues are, A's eigenvalues are 1, 1, and the other one is lambda 3. Lambda 1, lambda 2, lambda 3. We do not know the third eigenvalue lambda 3, right? But we know one of the properties that it is lambda 1 plus lambda 2 plus lambda 3 equal to sum of the eigenvalues equal to trace of A. This is first property of the eigenvalues. Therefore, 1 plus 1 plus lambda 3 equal to trace of A is sum of the principal diagonal elements 2 plus 3 plus 2. It is 7. So therefore, from this you can write lambda 3 equal to 7 minus 2, 5. So the third eigenvalue is 5. Therefore, the eigenvalues of A are 1, 1, 5. Then what are the eigenvalues of A inverse? So if you know the eigenvalue of A as lambda, the eigenvalues of A inverse are 1 by lambda, right? Just taking the reciprocal. So here it is 1 by 1, 1 by 1, 1 by 5. Therefore, 1, 1, 1 by 5 are the eigenvalues of A inverse. So none of the eigenvalues are 0. Therefore, A inverse is possible and A inverse eigenvalues are also possible, right? So that is the end of the lecture 10. Please like the video, comment your feedback, and whatever topic you want to learn, you can comment in the comment section under the video. Please share this video with your friends, and thank you. Please subscribe to our channel if you have not subscribed yet.